Okay, welcome back. Hope everybody is doing well. We're back in class. Can please somebody log into the Zoom to make sure that I'm audible and we're recording? So hope everybody is well. How did the homework go? Any problems, any roadblocks? No?
Yeah.
Yes? Yeah.
So I had done my work and then I found out that for one of the questions we wanted the mean for every price.
Yeah.
I thought that it was mean for price.
It is mean for each price group, but it's the mean of income for each price, right?
Right, so I didn't do that.
Okay.
Okay, so I just played it now.
Okay. So if you want to resubmit it, then I would resubmit it. I still can give you some points if you want. Yeah, let's do that. Okay. Any other roadblocks?
It took me a very long time.
It's what?
It took a very long time.
Well, it's a homework, right? You had like almost 3 weeks.
I'm just saying it took like many.
You gotta see it from that point. You did it now. It was super annoying, but you will remember this for the rest of your life. In some shape or form, you will remember that there was something I asked you to do which was super annoying and took super long. And this may resemble that you deviate and calculate the deviations from the mean. Okay, so I hope it wasn't too complicated. It took a long time, I'm sure. The subtractions takes a little longer, but it's overall it's a good exercise. Hi, Marcelo. Yes, I waved back. Hi. Okay. So you're remote today. Are you quarantining?
No, I just thought that class was on Zoom. It was like too late, so I
Yeah, I
just
can't
joined on
hear
Zoom. I
you.
hope it's okay.
Okay. So, but you can hear me well, right?
Mm-hmm.
Just not if you understand me. Good. Okay. Please, if you don't attend class, please let me know beforehand. This is an in-person class, and I'm advised to treat this as an in-person class. So just in general, let me know before if you don't attend. I'm not too overly picky on attendance, but it's an in-person class, and as such, I'm asked to actually do assess attendance, which will keep on forgetting where to do that. Yeah. Okay. So Jocelyn Cohn. Hi. Don't be angry if I don't remember right away. I'm trying. I'm really trying hard. Yael Benenbaum is here online, and this is.
Hi.
Hi. Eden, I've seen. Abigail Goldberg. Oh, hi. Yes. Okay. Slowly but surely. Evie Gutlove. Yes. Hi. Elena Hickton. I've seen. Yes. Hi. Marcella Homseny is online. Shana, I've seen. Hi. Amira, I've seen. Hi. Hannah Pupko. Hi. Am I pronouncing your name right? Yes.
Yeah.
Okay, great. Lizzie Zucker, I've seen. Hi. Okay. This decimated is like you're like a task force. Thanks for staying on. Okay, good. Let's do this. Okay. Good. There's a chat message. Okay, good. Okay, we'll do that later. Good. Today we're going to continue what we started off last week. So first of all, so we're back in person. I hope everybody of you is feeling well and all went well. It was a precaution to kind of do this as a remote class on Wednesday, and I think it was the only reasonable thing to do. But in principle, we're back to being in class now. Good. We will be talking about the normal curve sets course, and today we're starting hypothesis testing. So we do hypothesis testing today. And we will, on Wednesday, we're going to talk about confidence intervals, which kind of meshes into the topic. And bless you. And this will be part of the midterms that we're writing next week. So the midterms are going to be in the same format as the quiz. It's going to be in person. It's going to be here in class. And you're going to start in class simultaneously the quiz online on Canvas. And yeah, it's 1 hour and yeah, you're going to do well. I'm not concerned. Just do the practice quizzes, study the material, do the homework, review the homework, what was done. It shouldn't be harder than that. You should definitely do well. Yes.
What day did you say the midterms are?
Wednesday. It's the 3rd of November.
The next week Wednesday?
Next week Wednesday, yes.
And what is it? It's cumulative, so like what we did last classes, or
Yes, it's up until Wednesday. So confidence interval will be part of it. And Monday we're going to do a review session. So the review sessions are usually designed in that way that we fly through the slides. And whenever you see something you want me to talk about, you want me to explain once again, I'm going to explain it once again. So it should be straightforward. Any questions? Yes.
is your final including material from before the midterm?
Yes, it's going to be cumulative. It builds up, right? It's not going to be, I'm not going to quiz you for the first things with much weight, but it's going to be each part will contribute to the final. But with the practice quizzes, you get perfect starting conditions. You're going to be fine. Yes.
Are there going to be any open-ended questions, or just almost?
There may always be some, but it's not the norm. Usually it's blanks, fill out the blanks, it's multiple choice. You've seen it, right? And basically a directed question on calculating something. And it's randomly scrambled, so I can't promise what's exactly going to be, but I think this is the fairest approach. But if you do the practice quizzes, you have seen every question. It's a lot of questions, I know, but it's a very convenient way to essentially approach it. Yep. Yes.
In person, but on Canva.
Correct. Yes. I don't like paper, so so I rather save the trees. Yes.
How much does the midterm count in the final grade?
We can have a look at the syllabus. Let's do that. Marcella, yes, I see you raising your hand. Bear with me a second. So we have here, as per the midterm, we have, as per the syllabus, we have next week, Wednesday is the midterm. You see the grading scale here, and you see here the weight of the midterm, and the midterm is weighted at 250 points. So it's a fourth of your grade, essentially. So the scale essentially is here. The quizzes, each quiz, this is just testing the waters, right? This is for you kind of seeing where do you stand with your insight, and for me to see where you stand and intervene if necessary. Then the practice labs, that's bonus points. That's just basically it's a present for me. Then we have the participation. That's the discussion entries. That's the discussion comments. Please take those serious. It's still 50 points. Then the homework counts also a fourth. And these are the exercises in the shape and form as the homework was. The first one is a little bit of a learning curve, and it comes as a shock. You're not the only ones. It's a lot of work and it's annoying. I know, I understand. But the other one, the next two are not going to be as terrible. There's still going to be a lot of work, don't get me wrong, but it's easy and it builds much smoother on the class per se. And then we have the midterm with 250 and the final exam with 250. So overall 1,000 points you can reach, and the grading scale basically will then show where you stand. Is that answering all questions? Any other questions? Yes, Lizzie. Oh.
Which chapter is it? Like, are we going to test it on the midterm? Like, which chapter does it end at?
It goes until chapter 8. Confidence intervals is chapter 8. All right, so the question was up until which chapters it includes the confidence intervals for those online. Yes, Marcella. I don't know how to put you in speaker. Maybe let's do chat. Can you chat the question to me?
Hello, can you hear me now?
Hello?
Okay.
Hello?
Okay,
Sorry, I having trouble hearing. One
so I
second.
can't put you on speaker for some reason. I don't know how to do that. But no. Can you chat the question or send me an email? I answer it or put it on discussion board. Okay, Marcella? Forgive me. I'm not sure how to get this here. All right, good. So, but let's get started. Or did you drop it in the chat? Write me the question. I'll answer it now or later. Okay, as said, today we do hypothesis tests and confidence intervals on Wednesday. Monday, a review session. That should be fun and should be insightful. Prepare questions, come with questions, bombard me with questions. On Monday at midterm, at the same time, 6:20 to 7:35. It shouldn't take that long, so you're probably gonna get home earlier. Okay. Good. Chat, there's a new question. How many questions will be on the midterm? You're hitting me unprepared. I think it was 30. I think you have 2 minutes for each question. You have 30 questions to answer. Yes, Hannah.
On the first quiz, you took off stuff from chapter 1 down.
Once again, please.
You took off stuff from the first quiz from chapter 1.
Yes.
Will that be on?
It will be from 1 to 8. It will be all the chapters.
No, but on the first quiz, we had learned some of the information, so you took it off. But it comes back.
It comes back, yeah.
It's like
Yeah, it's always cumulative. So it builds up, the whole class builds up. It's unfortunately statistic kind of, it goes step by step by step. All the tiles come together and
I don't
that's,
think we learned it though. Like the Z table and those.
Yeah, and like ANOVA testing, we didn't learn that.
yeah, the ANOVA testing, that ANOVA, yes, the ANOVA question, forget the ANOVA question. Yes, that will not be on the question. I actually excluded this question. But the question of the ANOVA, that was really just, and we have talked about it in the first class. So I didn't fight that point. Who brought it up? I'm not sure anymore. But yeah, so it is basically just asking for the application. When do you use which test? And we talked about comparative and correlational methods. And then the ANOVA was mentioned, but doesn't matter. I took the question off, it's off the table. And it was just one question, but it's, yeah. Okay, good. How many questions? We talked about that. Okay, Marcel, it's 30 questions. The estimate is two minutes per question. That gives a total of 60 minutes. And as such, the canvas just will be administered. Okay. If no further questions, then let's talk quickly. Let's recap the normal curve. So we have talked about the normal curve last week. Normal curve is a symmetric unimodal and it's defined mathematically. It's a function and you basically can assume that all the area under the normal curve adds up to a percentage of 100%. So the entire population is captured under this normal curve. And this function also can then serve to essentially allow for you to quantify with each set score how much of the population is captured within that set score between the mean or between two set scores or from the set score all the way to the left. And this is essentially which we talked about in the context of this, where we basically have a set of 0 is essentially where you see the mean. Arithmetically, it's defined, you calculate the set score as the individual point minus the mean divided by the standard deviation. That's how you arrive at the set score. Yes.
So any point that's to the left is going to be a negative z-score?
Yeah, exactly.
Anything where it's going to be positive?
Correct. And this is where we discussed the set score table. And maybe this is the time where we essentially can look at the set score table. So we have here the set distribution. We have the mean splits the normal curve in two parts. We have to the left, we have negative set scores, which essentially comprises 50% of the population. We have to the right, we have the positive set score, which are the other 50%, which have a value of whatever variable you look at that is above the mean of that very variable. If you look at the set scores, and we will need those set scores today, if you look at the set score table, you essentially see that this set score table is essentially exactly structured this way. So you have here at a set score of 0, you have 50%. The further you go to the left, the increments are basically declining. So the percentages decrease. So when you imagine the normal curve, the further you go to the left and the set score, the negative set score gets smaller and smaller and smaller, meaning that the negative value will increase. You come here from 0 to minus 0.01, minus 0.02, minus 0.03, and you come from 50% all the way at minus 0.09, you come to 0.46, which is essentially left of minus 0.09 to the left, or the negative values, will essentially comprise 46% of your population. So this is how you essentially have to look at this. Arithmetically, this obviously goes then in the same direction. So if you have two set scores and you want to calculate in between those values, you have a set of 1, you have a certain percentage at a set of 1, which essentially when you look at the set score table, this set of 1 would, for example, be here 0.84. So this is 84% of your population are being contained from 1 all the way to the left. So if you are now looking at minus 1 essentially you will find here. So that's 16% approximately. So you have 16% of your population will be to the left. So now essentially you have 84 minus 16 will now essentially comprise, and we have learned that within one standard deviation plus or minus, you have 68% of your population. So 84% minus the 16% gets you to 68%, right? Remember that? And this essentially is how you can arithmetically approach the set distribution. The set score is calculated as x minus mu divided by the sigma, gets you essentially to calculations where you can now calculate the set score for each value on your entire x-axis. You can arithmetically look at everything to the left, everything to the positive, which we will do today. And you can essentially also back transform set scores, knowing the mean, knowing the standard deviation. You can obviously arithmetically also re-transform them into the actual value. So this is how you transform them back into raw scores. So essentially you have the x is your random variable. That's your essential raw score. The set is the set score that you have arithmetically derived at by calculating the set by x minus mu divided by the sigma. And your set multiplied by the sigma plus the mu will get you to the raw score again. So you're back at the x. So you're just rearranging the formula, and you have different variables at your disposition, and you're calculating the x. You're calculating the raw score again. So we talked about this normal distribution. We talked about that. So you're using this essentially as a standardization tool to basically compare two variables that naturally in their magnitude wouldn't correspond well. The example that Nolan and Heinzen have chosen here is by standardizing all emotions and the emotion fear and the emotion disgust over the years from 1900 to 2000, and essentially allows to characterize distribution in a population on a standardized scale where basically you can compare different variables that do not have a comparable scale. That's the idea. you can transform z-score into percentiles. This is what we essentially did. Everything, the definition of a percentile is if you have a percentile, it goes from 1 to 100, everything to the left of this percentile essentially captures that part of that population. So if you have the 50th percentile, you have the mean, which essentially comprises 50% of the population. If you have the 75th percentile, you have 75% of the population. If you have the 25th percentile, you have 25% of the population below this value. Can you remember the interquartile range as a marker of variability? That essentially quantifies the 25th and the 75th percentile. These you could also express as z-scores, and essentially would also for you to allow to approach this in the same fashion. So the z-score and the percentiles are closely related because the percentiles are essentially contained here in your z-score table. And this is what we will be discussing today, where you actually calculate percentages back to z-scores. This is one of the basic procedures for the hypothesis testing. So the normal curve and the percentages, we talked about this. We basically have, and we have discussed it before, with 84 minus 16, with 68% of the population within one standard deviation below the mean and one standard deviation above the mean. So plus one standard deviation, minus one standard deviation will capture 68% of your population. Plus, minus two standard deviation will capture here 48% of your population. Plus two standard deviation here, those 48% of the population that are greater than the mean. Together, this is 95.7 on rounded 96% of your population within two standard deviations. And three standard deviation comprises 99% of your population. It's the empirical rule. We discussed it in the same context. Yes?
Can it go above 3 or negative?
It can, yes. So 3 comprises 99%. So 99% essentially will capture, the 3 standard deviations will capture 99% of the population. 100% of the population you have was the minimal value in your entire population over the maximal value in the entire population. This is in the context of a sample not really achievable. You would need to measure the entire population to really get to this 100% coverage. So it's unlikely that this will be possible. Yes.
Example. Could you give an example of using, like, why do I need the percentage for?
Well, we will need it for the hypothesis testing. One example in the context of hypothesis testing. So for the microphone, so essentially the question is an example why these percentiles are actually important. So there are various examples where percentiles are really important. One example is for example in pediatric medicine, you would follow percentiles of children at various ages, and you will see the growth of babies over time, and you will follow them within the percentiles of the population with a certain margin and variability around these percentiles. So you compare the baby in front of you, because it's constantly growing, to the percentiles of a population. This is why a percentile is important, because you get a characterization of the population at a certain condition of interest in the context of a baby age. So this is why percentiles are super important. Another example, for example, would be for hypothesis testing, where you have a sample that you essentially, you draw from a population a sample. That sample has a certain characteristic and has a certain kind of composition in terms of comorbidities, age, gender, race, you name it. And you want to compare your sample to your population. So, and this is what we will be doing today. So we have, for today, we're going to be discussing set statistics. Basically, set statistics means that we know the population mean. We know what the mean of any random variable in the population is. We know what the standard deviation in that population is. And we're trying to figure out whether our sample is at a certain probability is different from the population mean. So when you have your sample, you're taking the variability and you're using this variability on your sample, on your 100 randomly drawn individual, and you're trying to figure out the probability with which this sample is significantly different from the population mean. That's another example. Very specific, but we will work towards that today.
These are terms like the normal curve and the t-square and all of that. It's only relevant in like observance statistics, right? Because in an experiment, you're calculating relations of the
Yeah.
effect of one thing and another. It's also about the population. So
Yes. That is a very specific question already. Is good question, good comment. So the question is whether it's relevant only in observational statistics or also in experimental statistics, and it's important in both. So the normal curve is essentially a basic assumption of every statistics we're currently discussing. Sample statistics are also conducted under the assumption that the sample is normally distributed, meaning the shape and form allows then for certain arithmetic procedures that allow the statistics to be conducted under the assumption that these are normally distributed variables. And the set score, it's not a set score anymore when you deal with a sample, it becomes a t-score. We will be talking about that after the midterms, but the t-distribution means to resemble a set distribution, which essentially again acts under the assumption that all this data is normally distributed. It's very specific now, but essentially, I gotta disagree with your statement because it's also then important when you deal with samples, because you still, also in experimental settings, you still have samples that you're comparing, and essentially those still act under the assumption it's a normal distribution for these concepts to apply there. But it's a good comment, very advanced thinking, thank you. Any other questions? Okay, let's carry on then. Okay, normal curve and percentages. So we can characterize the normal curve based on the set scores. We have, based on these standard deviations, we get the set scores 1, 2, and 3, and further. But basically, in a population, in a perfect setting, you only have 3 standard deviations, but in samples, this is actually not the case. So practically, you will, not see 100% coverage. The central limit theorem, and we talked about that, relates now the variability. So first of all, it says the central limit theorem says that the distribution of the population creates a mean that is identical with the mean of your sample, particularly when the sample size is large. So the larger the sample size, the more likely your mean, your sample mean, will be identical to the population mean. It further states that the standard deviation of the distribution is less than the standard deviation of, so the standard deviation of the sample, of the distribution of the sample means is smaller than the distribution of the scores in the population. And for that very reason, we mean to now come from a population level on the distribution of the sample means level. So we're only assuming that we're drawing repeated samples from that population and we're building a distribution of the sample means. And this is what we are working with. And this is what we're using for hypothesis testing. So the way you're thinking of that is essentially that you have a population, you have the US population, and you want to understand whether a sample that you draw from your population essentially is significantly different from this population. And you're comparing this under the assumption that your sample mean is a mean that you derived at by drawing repeated samples from your population that build up this mean that is identical to whatever resembles these randomly drawn means. And this is identical to the population mean. You will then essentially use the standard deviation from your population to calculate the variability of this distribution of the sample means. And you use this variability of the distribution of the sample means to test whether your sample mean is different from the population mean. And for this, you need the distribution marker. And this is the standard error of the mean. Depicted here is a sigma m, which essentially relates to the standard deviation of the population divided by the square root of the sample size. So essentially that gives you the standard error of the mean. And this is the standard error of the mean. This is the variability of the means that have been derived from your repeated samples. So you get by that, you get a normal curve that reflects all the means of all these samples that you have randomly drawn from your population around that mean that you have in your sample, which means to be identical to the population mean. Does that make sense? So we're going away from the raw score of the samples. We're only assuming that we're drawing repeated random samples, and these repeated random samples have a number of different means, and these will have a distribution that essentially will allow for us a characterization of these sample means using the standard error of the mean. And this is what we will be using for hypothesis testing today. Okay? Any questions on that? It's a little abstract, I understand that. So if you have any questions, please really, now is a good timing. It's all about probabilities, essentially. So what you mean to create here, so you remember the example with the happiness scores. We have here the population. These are all the happiness scores. And now we're drawing repeated samples, and we did that in R, you remember? You get repeated means, and these means build a distribution that is narrower than the population distribution, but essentially is now showing a spread of the samples that you have drawn, but only the means, not the individual scores anymore. Means have the advantage that when you deal with repeated sample means, you essentially get a normal distribution that essentially removes skewness from your data. So here you have, for example, you have distribution of scores in a population. And when you have a distribution of means with low sample size, you essentially still get the same skew. But if you increase the means of greater samples, you essentially get closer to normal distribution, which is the third rule of the central limit theorem, that when you increase the sample size, your distribution of the means gets more normal. It resembles closer a normal distribution. Yeah.
When you say distribution of the means,
Yeah.
you mean like taking, if you have like a graph or data, you're just taking random.
You take random samples. That's the assumption.
Take the mean of random sample.
Of each sample, yes.
Not for each sample.
But you don't really do it. It's an assumption that you're doing for hypothesis testing. So you basically, you have this real distribution of scores. These are the actual scores. These are the happiness scores. And then you build this distribution of the means under the assumption that you draw repeated samples, and you take that mean of your sample and you use the standard deviation that you know from the population to essentially build the distribution of these hypothetical sample means.
What do you mean making a mean for each sample? Because you need to do it with something. You can take one.
You're just taking one, essentially, you only have one at your disposition. This is how it's done in real life. And this is the hypothesis testing we will be doing today. You only have one sample at your disposition and you have one mean from your sample. Then you have for the set statistics, you have the population mean given, and you have a population standard deviation. So you have the real standard deviation in the population. Then you're taking this population standard deviation and you are calculating a standard error of the mean. The standard error of the mean is calculated as the population standard deviation divided by the sample size of your sample. So if you have drawn a sample of 30 individuals, you assume, knowing the population standard deviation, that the distribution of that means, if you would have drawn 100 repeated samples, you would have a standard error of the mean that relates to the standard deviation of the population by a division of the square root of the sample size. So you're relating one to another. So basically the variability so when you draw a sample, this sample will be subject to variability and spread and shape and form in its distribution that is related to the standard deviation of the population, because you will pick from every value of the population. So the standard error of the mean will also essentially resemble to some extent, or will to some extent relate to the spread in the population. So this is that relationship that you mean to build. So you're saying that this mean that you calculated from the sample is essentially also varying. So if you would draw 100 samples, there would be some distribution in there, which essentially is related to the standard deviation. And this is how you quantify this. Make sense?
Like each sample contains lots of
Scores, yes.
good scores.
And these scores build a mean together. And this mean is under the assumption identical to the population mean. That's the null hypothesis that you hypothesize. And the distribution of these means around that sample mean is essentially relating to the standard deviation of the population. Yeah. Okay. Well, it will get clearer with hypothesis testing, but as long as you're on top of this concept for now, I think we can build on that. Okay. The set formula in that context is essentially doing the same thing. So now we're walking away from characterizing populations. Now we're characterizing distribution of the sample means. And we're characterizing these distribution of the sample means by knowing a sample mean, a population mean, and a sigma m, which is the standard error of the mean. So we're characterizing this set score essentially by raw scores from the population. So they're standardizing the raw score from the population, not knowing this distribution of the scores. So we're trying to relate now and characterize now the distribution of the sample means with the standard error of the mean. So we're doing the same thing as for the population, but with the standard error of the mean and the sample means. So doing this will essentially get us a distance from the population, right? So if we have this mean subtracting the population mean, this will get us a difference. This difference has a certain set score characterized as the standard error of the mean, divided by the standard error of the mean. And this is the story with the cheetahs, right? You remember that there was 1.96 is our 5% threshold for significant differences, which we will be touching on today with the hypothesis testing. And there was meant to be identification of additional cheetahs because people tend to report results that are statistically significant and basically pushed over. But yeah, more about that today. Okay, so this was the recap of the normal curve. Now let's start with hypothesis testing, and now bringing this into practice will make things a little clearer, I believe. Okay. Okay, standardization is done to allow for comparison between variables that are not comparable as per their magnitudes. The set table allows to quantify percentages of scores between mean and any given set score. And so when we want to calculate now percentages associated with a given set statistics, so we're converting a raw score to a set score. So we're having a raw difference between our sample mean and the population mean. And we're looking up that area in a set table. So this difference has a certain position in this set table. And that will essentially be the difference between the mean and our set. So in the same fashion as we have done to find percentages based on a set score, you can also find set scores based on the percentages, right? If you, for example, are interested in a certain percentage, which we talked about, hypothesis testing having a threshold of 5%, the 1.96. You remember that from last time, right? So if we are looking for a percentage of 5%, we would need to look for 0.05. So if we start here with minus 3.4, well, we basically have a very small level. So that's 3.4 standard deviations from the mean to the left. So if we go now further to 2.4, 2.49, that would be 0.064. So that's 0.64%. If we're going now to 1.99, we're at 0.0233. If we go to minus 1.96, we are at 0.025. And this is an important value because I talked about this 5%, 5% or 1.96. This is 1/2 of those 5%. And now we will be talking today about hypothesis testing. And we need two-sided hypothesis testing. We need 2.5% on both sides. And this is why 1.96 is that threshold that is being used in the examples of identifying the cheaters. You need to distribute the 5% to both sides of the normal curve because it's symmetric. So the probability of finding differences in a sample to any given value will essentially be done in a two-sided setting where I assume both sides to be equally important. So, but now given the slide of Nolan and Heinz, and what is really important here in this context is that you can find any percentage on this set score table, and you can identify any set score that corresponds with each given percentage. So you can do a reverse lookup, so to say. Those are the cheaters. This is the one. So this is the percentages to set scores. So basically you can calculate set scores in the way and fashion we have seen before. Now you can also backwards looking at percentages and find the corresponding set scores. So if you look, for example, here at these percentages between the mean and the set, so they have a different set score table. So yes, Elena.
Are we ever going to be asked to find the specific Z-score? And if so, are we going to have a given table?
Yes, yes, yes.
Okay, so we'll always have a table to figure it out. And
no, it's well, it's there's one on Canvas, right? So we're doing open book.
Okay.
So you're fine. So you will have all the material at this position. So there's definitely the set score table. So I have uploaded the set score table that is somewhat different from the one they are using, but it's the same concept. I just find that one I uploaded more intuitive because having one that basically counts from the mean backwards, I find that a little counterintuitive. But just get familiar with the set score tables and know how to look those up. Yep. Yes, Amira.
Can you explain how the table works again?
The what?
Can you explain how the table works again or not?
Yes, absolutely. So we're just quickly recapping the table. Okay. So we have here the negative. We have a negative part of the table is on 2 pages, right? You have on this table, you have the negative sets, comes from 0 all the way to minus 3.49, which is kind of the maximum depicted here. It starts with a really small, and these are not percentages, these are proportions. Keep that in mind, please, too. So this comes from a proportion, goes from minus 3.49 to minus 3.4. Starts then again here with minus 3.39, goes to minus 3.3. So it goes essentially in these kind of form and fashion, all the way down to here, where you essentially have minus 0.49. And you see that this percentage or proportion here is increasing with every step to the right. So you're basically, when you envision the normal distribution, and I encourage you for the midterms, take a sheet of paper, map out. Don't bring the sheet of paper pre-printed, please. You can map it out on any sheet of paper. Map it out here, that you know how you're going, how you're basically looking at this. So when you're being asked, for example, to characterize a certain part of the population, make sure you're asked to have 2 set scores, and you're asked to calculate the percentage between 2 set scores, for example, like we did before with the 84 minus 16. Make sure that you have that normal distribution mapped out, and that you know exactly where's which. So if you have a negative one, you find that negative one, you have the percentage, then you find the positive one or the second value, and you're just calculating the proportion in between these two. You're subtracting the smaller one, the smaller value from the bigger value. That's why I find this one more intuitive than the one was going the distance from the mean. I hope you agree. That depends on the question. So the question was whether we were going to look at proportions or percentages. And this is, I also got to tell you, like, read the question very, very carefully. So the Norton and Heinz questions, some are a little tricky, but they're usually quite straightforward. You just got to carefully read. So they're not mean. You could make those much meaner. So that's what. So you could probably speak to some students of my first class, because back then I did the quizzes myself, and they didn't like me after that first quiz. So Norton and Heinz is they're not mean. So it's just read the question, make sure you have seen proportions or percentages, and you know what is being asked from you. But yeah, it's proportional. You know how to calculate. It's just basically multiply by 100, right? You multiply by a constant, and that's the difference. I would even go as far. I would still give you the points. Run this book. If I go over it and you have the right proportion and there's a percentage asked, I would still give you those points. So again, just like with the quiz, I will go over every question, and if there are any ambiguities or anything that you want to contest, write to me, let me know what you're contesting, and then we can have a conversation about it. So usually there's not much ambiguity in the question. There may be some, but not much. All right, does that answer the question with the set score? Good, all right, good, next. Okay, PowerPoint is now right here. Okay, good. Okay, so this is the set score table as Norton and Heinz wanted. So they also recommend to sketch the normal curve, and it makes a lot of sense to sketch it out because it just gives you an easy overview, and you avoid it. Sometimes under an exam situation, you're more prone to make an error just by I don't know, nervosity and like, well, it's not an oral exam, but it's still, you could be nervous, and from that end, it makes sense to sketch it out and to kind of be very focused in your thinking. Standardized C distribution, we talked about this, 68%, 96%, 99%. They rounded a little more than I would. So when you have a situation like that, you essentially also read the question whether they want the entire population to the left or whether they want only the distance from the mean. Like if you have a mean of 0.98 like they have here, this is 33.65% from the mean. If you ask to quantify the 0.98 all the way to the left, you have 50% up to the mean plus 33.65. So this is 83.65. If you want the inverse, if you want everything greater than a certain value, you have to calculate 1 minus the proportion you're looking at. So if you have 1 minus 0.8365, you get those 16.35 that are above the 0.98 pi. So this basically allows you to kind of see which proportion of the population is greater than a certain value. If you want to have percentages, and now we're coming towards the hypothesis testing, because hypothesis testing, you're comparing your sample to your population. Knowing the population mean, knowing the sample mean, and knowing this population standard deviation that you're equating to the standard error of the mean, which is the variability of your distribution of the sample means. So now if you want to have an idea to get percentages that are at least as extreme as individual scores, you can calculate it by essentially taking the negative set score and the positive set score. In between, you have a certain percentage of the population. And when you want to quantify the proportion of the population, the percentage of the population that is as extreme or at least as extreme as that particular set score of interest, you can quantify everything to the right and everything to the left of this set score. So if you have 16.35 here and 16.35 to the left, you basically have 32.7% of your population has a value as at least as extreme as the raw score that is corresponding with a set score of 0.98, positive or negative. And this is the definition of a two-tailed testing, a two-tailed quantification, because you have two tails in a normal distribution, a tail to the left and a tail to the right. And these two tails contain a certain fraction of the population. And when you assume this to be symmetric and you define one set score as being the set score of interest, you can basically quantify the proportions that are at least as extreme as that set score to both sides. It's important for the hypothesis testing because now, not yet, because we will be quantifying the probability of a sample being drawn from a population and being different only due to random chance or because the sample is really different than the population mean. This is what hypothesis testing with set statistics is going to entail. We'll talk about this in a second. Okay, calculating score below the mean. Yeah, so you come, okay, we talked about this, right? So you convert the raw score to a set score, you calculate the percentile, you calculate the set score, you look up the percentile on, you calculate the percentile, you calculate the percentile from the set score table, you get the percentile, or you can calculate it in R as well as in Excel, you can calculate it. You get the percentage below, you get the percentage above. You can also use the percentages that are at least as extremes as the negative and the positive, just like we discussed. And yeah, so this is the example of Manuel's height, which is an example that's in your textbook. Yeah, so we talked about this, right? So we have a set score of 1.82. So this is Manuel's height. So he comes from a certain population, and he had a height score that is corresponding with minus 1.82, which essentially gets us to a percentile of 3.44. So 3.44 of the population are smaller than Manuel. So this is an actual score that essentially was converted into a set score and allows us to quantify a certain percentile. And we will have a couple of examples on that. The inverse is also possible. Once you have that 1.884, you basically have 3.44, and you have 1 minus 3.44 gets you to 96.56. We're calculating the inverse under the assumption that under your normal distribution curve, under your function, everything is 1. So the entire universe of your population is quantifying to a 1. And the subtraction of a particular set score will allow you to get the inverse. Gets you everything that is greater than that set score. Any questions so far?
Well, do you have examples of questions that would be on?
We're going to do, as soon as we're through hypothesis testing, we're going to do examples. Yes. So same example. So we want now percentages that are at least as extreme as the set score of Manuel's height. So Manuel was a set score of minus 1.82, only larger than 3.44 of the population. So if we assume a positive set score of 1.82, and this is two-sided hypothesis, and this is then two-sided testing again. So you want a value that is as extreme as a set score of 1.82, whereas this will correspond with a different value. It's a much higher raw score, right? But quantifying it in a two-sided setting essentially requires you to assume both percentages to be taken into account. So essentially you have everything that is as extreme as a set score of 1.82, negative and positive, is going to be 3.44 multiplied by 2, which is 6.88. Use case. You asked for a use case, Eden, right? So the use case here that they used is from a dating app, men's appraisals of women's attractiveness, basically kind of steadily increasing, and the percentage only declines was the highest ratings, whereas there's a clear decline in women's perception of attractiveness of men. And the way why this is important, and the reason why this is important, because it deals with different population sizes, right? It allows for you to essentially quantify things in a way that you equate percentiles to within populations that are of different sizes. And this is why set score statistics and set statistics is important, because essentially it takes away from the actual population size and the actual individual count. So basically it deals only with the percentiles. So now, yeah, same example essentially here. You have a percentile that you're interested in. So you want to have 63% corresponding with 0.33 is, yeah, it's the same approach, right? You basically have 0.33 corresponds with 13% or 63%, which comes from the set score table again. So everything below that will be smaller than the raw score corresponding with 0.33 set score. Yeah. And now we're getting to the standard error. So now set statistics for groups. So we have now a sample that we have drawn. And now we're dealing not with individual scores anymore. So we're not dealing with Manuel's height anymore. We're dealing now with means. And this comes now to a distribution of the sample means. And now when we remember the happiness score, we had all the happiness scores together build up a population of 256 happiness scores that had a very wide variability. Now, randomly drawing these samples and building a distribution of the sample means essentially gets us a narrow distribution where the mean of this distribution of the sample means is meant to be identical, as assumed and hypothesized to be identical to the mean of the population. And so we're using now the means, not the individual scores anymore. The samples of many scores are studied. And the mean and the standard error is now becoming essentially what we will be using to classify the set scores. So we're classifying now set scores of the distribution of the sample means rather than the actual population. So we're not quantifying at this point any more individuals in the population, like we did with the standard deviation of the set scores. Now we're quantifying probabilities of that distribution. So we have a distribution of the sample means, and we have the sample means are basically characterized by the mean, which is that one sample mean that we have at our disposition, and the standard error of the mean, which is calculated by the known standard deviation from the population divided by the sample size, the square root of the sample size of our sample. Okay. And you're approaching it in the same fashion. You have the mean in the sample, and you're now trying to characterize, and I think this is now, yeah. So now this is where we can switch over to another example, which I think is a little easier to comprehend. And now we're doing the first hypothesis test, so to say. Maybe a little too early, hold on. Now let's stick a little long with this. Okay, so what you're doing in hypothesis testing now. So you have a sample and you have a sample mean. You get, with the standard deviation of the population, you get a distribution of the sample means. You get a variability of this distribution of the sample means around that sample mean. And you're using now your sample and your standard error of the mean as the variability of the distribution of the sample means to test the hypothesis whether your sample mean and your sample is significantly different from the population mean, meaning that it's different and not only randomly small different and not randomly different because of random sampling. And you're quantifying this as the probability that this was indeed a difference, that your sample is indeed different, and not just due to random error or random chance being drawn from the population and appears to be different. So you're quantifying this probability of this being just due to random chance, this difference you're observing between population mean and sample mean, right? So you have a population, you have a population mean, you have a sample, and you have a sample mean. There's a difference between your population mean and your sample mean. And you want to know whether there's a systematic difference between your sample and your population mean. And this difference can be due to random error, random chance. You drew 100 people from a population of interest, and that sample could just be different due to an error that you just took coincidentally 100 people that were significantly different in whatever parameter you were interested in. So the probability that this is indeed a significant systematic difference, you quantify with characterizing the distribution of the sample means using the standard error. And this essentially is hypothesis testing. So you're testing the hypothesis that these two means are indeed significantly different. Does that make sense? Any questions to that? Okay. So again, I repeat, you want to test whether the sample mean differs from the population mean. And this you can do under the assumptions that that sample that you have at your disposition is indeed randomly sampled, and it's not in any way from a certain subgroup in the population. And these assumptions are key to essentially make accurate inferences, which are drawing conclusions based on this difference and whether you have differences between your differences. So one of the main assumptions is that you have a normal distribution. So that basically leads you to a parametric test. You basically, parametric testing are essentially a statistical test based on assumptions about the distribution of your population. The difference to non-parametric testing, which we will only touch on one test, which is the chi-squared test, does not make assumptions about the population. So these are the differences between parametric test and non-parametric test. So the parametric test assumes a normal distribution, whereas the non-parametric test does not make any assumptions about the underlying population. Any questions on that? So the three assumptions that hypothesis testing makes is that the dependent variable is a scale measure. A scale measure is a measure that essentially is a continuous variable that essentially can take any point on a scale and is basically, yeah. What you cannot do, and these are tests that we do later on, you cannot break an assumption where it's clearly nominal or ordinal. That means that you need to have an actually continuous variable that essentially is either a ratio or an interval variable, right? Then the second assumption is that participants are randomly selected. This is what I talked about before, right? You need random selection from a population. That is one of the basic assumptions. And this is one thing that is quite often violated, essentially, as we talked in sampling and probabilities, right? The population distribution is approximately normal. That can, to some extent, be overcome when you have a sample size that is at least 30. That's this magical number of 30 that will come up in the context of hypothesis testing quite frequently. And essentially, as soon as you have more than 30 individuals, you can get away with parametric testing, although it may not be normally distributed. That is something to keep in mind in this context. So this is quite an important slide, which I would flag essentially for the midterms. For hypothesis testing, so again, hypothesis testing is testing the assumption, testing the hypothesis that the null hypothesis, where you assume no difference between your sample mean and your population mean for the set statistic. For hypothesis testing, you undergo 6 steps. First step is that you identify population distributions and assumptions, and you choose appropriate hypothesis tests. And this will remain the same for all the tests which we will do. For now, it's the set statistic that compares the sample mean to a population mean with a known standard deviation. Okay, we're identifying populations, we're identifying distributions, we're making sure the assumptions are met, and we choose appropriate testings. Then we're stating null and research hypotheses in words and notation. We determine characteristics of the comparison distribution, determine critical values or cutoffs. And this is now where my 5% come in, because we want to keep that probability of the sample mean being different from the population mean less than 5%. And this probability is basically quantified by the set statistics that is being employed, where we're basically assuming now a certain probability that are as extreme, but we will get to that. Then we calculate that statistic and we decide whether to reject or fail to reject. And this is now where we're getting to statistically significant. Okay, so these 6 steps are to be kept in mind. The critical value is essentially, this is where you define how much probability of a random error of just pure chance in your difference between sample mean and population mean are you willing to accept. And statistically significant means that the data differs from what would be expected by chance if there were in fact no actual difference. So this is exactly what I meant to say by the probability you're willing to accept that your difference between the sample mean and the population mean is due to random chance or error, random error. So this is essentially what you quantify then with your difference between the sample mean and the population mean divided by the standard error of the mean. Because you're quantifying your distribution of the sample means and the distance from that population mean. And that gives you the probability of this being really significantly systematically different from the population mean. And we will look at that in a second. Okay. So now I'm switching over to other slides. So I have a second slide deck on the module, which I think is a little better in outlining what I mean to show you. Okay. So why hypothesis testing? So hypothesis testing essentially, again, you are interested in whether there's a difference between your sample mean and your population mean. Why do you want to do that? Because you have a population mean that has a value that is either hypothesized or known. And you want to know, for example, if an intervention or a certain subgroup of your population is indeed different from that population mean. This is what you mean to understand. Questions that you would want to answer in this in this context is, for example, okay, so you're sampling from your population hypertensive smoking men and whether their cholesterol level is the same or is different from the general population, as an example. Forget the malaria example, that's too specific, that's an intervention. But essentially you are now approaching this hypothesis by so you are approaching this to create a yes or no scenario, a binary outcome. Either it's significantly different or it's not. And you're using this with a certain threshold, with a certain cutoff value. And you're basically quantifying this in a way that you are basically, you're meaning in your null hypothesis, you're basically stating my sample mean and my population mean is the same. This is your null hypothesis. And then you have, we talked about null hypothesis the last time, right? I believe we did last time or 2 classes before, I'm not sure anymore. Yeah, but we talked about it, right? So essentially you are assuming that there's indeed no difference. So this is our null hypothesis. So when you equate that to a courtroom, a defendant is essentially considered not guilty until his or her guilt is proven. And this is basically what the prosecutor tries to prove during the course of the trial. And this is basically where you get to the alternative hypothesis. So you are only accepting the alternative hypothesis when there's enough evidence rendering the p-value smaller than 5%. And you're getting here in the realm of, so if the defendant is indeed not guilty, and you're accepting the null hypothesis, then you have made the right decision. If the defendant is guilty and you're rejecting the null hypothesis, you basically get the right decision. But if you make a wrong decision and it's basically the defendant is guilty, but you're basically accepting the null hypothesis, you're basically running into a type 2 error. So you're not rejecting a null hypothesis that should have been rejected. If you are having a non-guilty defendant and you're rejecting the null hypothesis, you're basically getting to a type 1 error. But we will talk about that in more detail. Yeah, and that's nice to kind of keep it in mind. So type 1 error is basically where you have a false positive, where you're assuming something, or where you're concluding something that actually cannot be true. Whereas a type 2 error is a false negative, where you're not diagnosing something that is actually should have been diagnosed. It's a nice way kind of to keep it in mind. So how we're going to do now, essentially, this hypothesis testing. So we have a type 1 error rate where we are rejecting something that should not have been rejected. So we are assuming now that the difference we're seeing between the sample mean and the population mean is indeed a systematic significant difference. But if we're doing so, we essentially still have here a rest risk that our sample could still have been drawn due to a random error and just due to pure chance. And this is our 1.96 critical value. So everything to the right or to the left of minus 1.96 is our critical value. Remember the 0.025 that I mentioned before? This is our two-sided hypothesis with 0.025 multiplied by 2. And to bring this now into an example, so we talked about the steps in hypothesis testing. Oh, running over. We talked about the steps in hypothesis testing. And we're now calculating two-sided tests where we're coming on a null hypothesis, we're equating both to be same, whereas the alternative hypothesis says they're significantly different. The way we're approaching now the example of the blood pressure of smoking males from the general population with 211 milligrams per deciliter of cholesterol would essentially now lead. Okay. Yeah. Okay. Yeah, we didn't get far enough. Yeah, I will post the rest of this lecture online. Yeah, so essentially the hypothesis testing is being done by calculating test statistics in the way we have discussed earlier, by calculating X bar minus the population mean divided by the standard error of the mean. And by that, you're characterizing your distribution of the sample means. And by that, you're finding whether there's a significant difference between your population mean and your sample mean. And the example here essentially is that we are looking at extreme values, at values that are more extreme than our thresholds, that the population mean is still part of that sample mean and is essentially indeed was a probability exceeding the null hypothesis. Yeah. So the arithmetic example, I will walk through that again. I will post a little mini lecture on that, and we will talk about it again on Wednesday. So what you essentially do, you have your sample mean, and you subtract it from your sample mean your population mean. By that you get the difference between sample and population mean. And under the assumption that your distribution of the sample means relates to the population standard deviation. You're essentially dividing that by the standard error of the mean, and you're coming to a set score that characterizes the distribution of the sample means in relationship to the population mean. And by that, you're getting a p-value that is being read from the set score table in the same fashion as we have done for populations. And we're getting here a p-value, a two-sided p-value that corresponds with the set score we have derived from this equation. But I'll talk about this in more detail on the online lecture, and we will talk about it in more detail on Wednesday. Well, thank you. Sorry for running over. Have a good night.